developers, most of which are here. And that has to do with the auto test, with the samples directory. So if you look at central code samples, we have all these nice samples. And many of these directories, many of these runs are, as you all know, automatically run every night on 2 different servers, and some of us get emails when something goes wrong with these runs. This is our insurance against accidentally changing something in the pencil code that breaks the functionality that we have and that we need for all the, or maybe also new production runs. Now, there's a few things that can be optimized with that. And one thing that is irritating is that all of these tests together run typically about 2 hours, depending on the hardware, obviously, that you have. Well, not all of these. It's 25 of these that actually are run every night. And that takes about 2 hours, I think a bit more, including compilations. And that's long in a sense, but on the other hand, it's way shorter than any production run would be. And we have reduced the resolution to make this feasible, that any individual run doesn't run more than, I don't know, 5 or at most 10 minutes. 10 minutes will probably be so nice for the auto test, but if somebody wants to do some work and build their own production run on one of these sample directories, then they have no clue what resolution to choose. If they don't know what resolution to choose, or if they want to run it at a different resolution from what we have here, they will normally also have to, or want to, adjust the diffusive coefficients. If you have higher resolution, you don't need as much viscosity, magnetic diffusivity, thermal conductivity, as you need in order to get those stripped down, simplified, non-production runs stable. So basically there's information missing. If you start with one of these run directories, that's a good starting point in a sense, but there's a few things that you just have to figure out yourself. And that information and some other information like who wrote that thing or is responsible for that test has now been added to at least the run directories that are for the tests that are run every night, and the structure is like this. I guess Tony Lee would make this XML. We can always change if we like, but this is also easy to parse. So directory name, okay, it's obvious. The CDS ID is always nice. Who is responsible for the module? And my plan is to have the nightly auto test mail that person, even if that person is not on the normal mailing list for failures of an auto test, in case that their test really breaks. How old is, well, is it something recent or has it been around for a long time? Is it supposed to succeed? Hopefully if it's one of the 25 tests, that we can then gradually extend that to cover all the runs in the test directory, in the samples directory. And then you can write stuff like recommended resolution, and then probably in brackets you can put something like, I think in the console, you'll see that in the console directory, I just as a sample, I think the values are off, but I put an entry like recommended resolution, I don't know, 128 cubed or something, I think, we'll see. And then in brackets the recommended values for the viscosity and for the can't even get diffusivity in that case, thermal conductivity, I guess. And then you can add all sorts of comments, and a number of runs already had comments, and since I didn't pay too much attention to what I was doing, I actually managed to erase them and replace them with some skeleton for this, and fortunately Axel found out and resurrected the stuff that was there. So often we already had some comments, and Axel then also added, and that's a very good idea, a references section, so people can read up on more details and on parameters and so on. So this can be relatively short. So I'll now just go through these files And for all the files where we do not have a maintainer right now, I'll try to bully somebody into signing up for this. That's the point of this exercise. So, okay, this one has a maintainer. This one has a maintainer. I'm not maintaining all of them. Unless Axel put my name into all of the README files. No. So, force boundary. That's actually something I coded, so if anybody wants to take over, that's fine, but I think I'm sort of morally obliged.
Is that related to Sven Bingert's simulation?
It is, yes, actually, that's why I didn't put my name there, because I was hoping that you would say, I do it. Yeah, great. And then we can add the exact email and everything later, and think about how to obfuscate it such that it cannot be harvested by robots from our subversion repository. Cosmic ray.
What was that?
Who was that again? That was
both me and Snodden. Andrew Snodden. You can put Andrew Snodden there first. We can fill up.
Okay. Random EU particle.
It's been a while, yes. I'll do that.
Yeah, actually, if Vlad is not here, we can assign a bunch of stuff to him. Okay.
That's common.
By the way, your ID is written with capital D, the D. That's not right. In your case.
Does CBS care? Or does it replace that?
Doesn't work. You see it didn't work.
Oh, yeah. Okay. It was no longer late at night when I did that. Interstellar.
Yeah, that's a problem perhaps.
We can put Tony there, but that's pretty pointless.
Not anymore. So then, you should do it or just go in. You could put me first. But that, of course, raises the issue of
multiple.
First of all, I think yes, like here we have, of course, multiple. But what I meant is the original developers of the module may be sometimes interested to know, because if I maintain, for example, this Interstellar, there's a bunch of things which are really just ideas where I don't have a good response to that.
Both maintainer and developer.
Original.
Or it would just be as a common field.
Well, it can be an optional field.
Oh, sorry, I couldn't remove that.
Like this.
But wait, it's all in different lines. Is there an easy way of grabbing this? It's not really possible. Suppose you want to grab from all these README files the names. Then
if you know, well, if you know how many, well, I guess you can do something like this. No, one line. You can do grep minus A4 maintainer. I'm not getting all of them. I would need to use fine for that, but just for the demonstration. Start README, and then you type, unless you have a German keyboard in front of you.
I could.
Okay, then you type to grep. This one, for example. That's relatively good.
Can you explain that again? What was that? So, grab? What does A4 mean?
A4 means print the line and the following
4 lines.
3 or 4 lines.
Oh, I see.
And, well, there are certain assumptions I'm making, but you can play with that. And then since essentially mostly the lines with the email addresses have the less sign, we can then prep for that. You know.
Okay, I understand.
Okay. So original developer told me, and there's no point in putting an email there. I guess. Well, putting it later. MRI turbulence hyper. Hyper sounds like Anders, but MRI turbulence could also be blood.
Or even Toby.
Yeah.
I mean, I think we should give it to you.
I mean, I can put several names there.
Put me that.
See you right now? No, then we can. Self-gravitating shear wave. I could have filled some of this in by myself, but then later people can claim that I did it wrong and that they are not responsible. Now they can't. Now we have many witnesses, and they'll have to sign that you've seen it.
Yeah. So here is really the issue that his test, and that's really unfortunate he's not here now, is always too big. It's a 2D test, of course. It's always too big for many machines. And then I made it smaller, and then he says it doesn't make sense if you run it longer, and it should be realistic. So he insists that this should be a physically meaningful thing.
Well, that's maybe somewhat easier now. If the test director really says you need at least that resolution, and I think in last case you would like, this is probably, did I put that there? If it's 2D, then obviously this can't be 120.
That was your default. It's 320, I think, right? Square.
Might be 320 squared. So he can put that there, and then we can have a really stripped down version in the repository, and then it's fine. I think currently this one is not one of the canonical auditors because it's so long.
Yes,
This is some 2D convection thing that probably the two of us did together.
This is not on the.
as you see, there's some comments already, yes. Is there any mention yourself? And also should maybe mention myself.
That should be also a place for the reference.
Hmm?
That before was a good place for the reference. Where you
Yeah, that should come in the last line then, of course, that's right.
yeah. Instead of this number, EN, whatever.
Yes, that's fine. There was an issue yesterday, somebody asked me in the hallway, what is Kelvin Helmholtz and what not? Maybe Anders can make a short comment on this? It was Petty, yeah? I hope, yes, Petty asked this question.
Chiral distribution.
What is what?
What exactly is Kelvin Helmholtz? The significance of density for variation. What is it? Is density and variation critical? I think the answer is yes.
Okay, so you define a Richardson number,
Mm-hmm.
right? And this will depend on density stratification. So stratification and
Yes. That's fine.
stratification and gravity will be stabilizing, and
Okay.
shear will be destabilizing.
So, okay, so it's a stratified thing. And I think the word Kelvin Helmholtz is often used in very general context sometimes, and it's
Just
not very precise.
any shear.
So yeah, we had a discussion whether a linear shear flow is unstable or not.
Yeah. That has nothing to do really with Kelvin Helmholtz.
What do you mean? I thought a linear shear flow would be unstable.
Yeah, but
But
for linear shear flow. But no, linear shear flow is only
It's not
non-linear.
linear, but it's still unstable.
Yeah, but only non-linearly.
Non-linear, does that mean you have to kick it?
For me?
Yeah.
And how much?
Yours?
Well, that
Yeah.
depends on the grams on that, it's a curve. Yes, it's not in that I did. It's me. In the complex strings, you put yourself, yeah?
Probably already had myself.
Yeah.
Yes. This it's maybe useful to actually really run these tests and also for longer. And then plot them and document what the result is. I mean, if you say recommended resolution, it may still blow up if you have never actually tested this.
Yes.
And then it should be documented somewhere. And possibly in ultimate, having to document that would of course be the so-called multi-author paper on that pencil code. But that's one possibility, which first they should be documented on some web page.
Okay, and
Wiki maybe actually.
I think it also helps people who want to do something new if they know the person that set the run up that they are starting with, and it's somehow easy to get in contact with the right people. So.
One issue is that we also stack physics onto some of these tests just to test the quantum physics. So then, for example, our turbulent test Gaussian is just a test Gaussian. So one would probably also write specifically you should probably remove the dust. You want to give pressure.
Yeah. All of this can go into the comments, and well, even with the explicit lines that you need to change in the make file of locally. Okay. Now to something completely different.
Can you check this in then already? Maybe because if you want to work on that.
While you're speaking. Exactly.
They remove it and take it out new. It's just number.
I'm going to show you. Yesterday evening we work with. And today I have this when I unblock. You know what does it mean? We work with the background after the class, and now
Was
we
your last
work
comment?
today.
What?
Hast du eingetippt, Eberfluss?
Well, it means that you don't have permission to this file.
So we should have written yours
I
then.
just see that one is free update.
Probably
Da ist
doesn't.
da alles,
Yeah.
was was sind, passt, könnte alles auch unter 3
Ja.
rekursiv.
And Wolfgang, some sample directory has no readme file.
Which one is that?
Delete the line or something like that.
Yeah, feel
Doesn't
free
mean
to
that
Yes.
fix that while you are paying full attention to
Where's the...
It's correct.
Unless
look
I
forward.
fail to
This or this.
find full screen.
This, there it is.
Okay. What I'm talking about, what I'm going to talk about now is work in progress, which sounds slightly better than it really is. It is work I have started and that I will probably not finish in the foreseeable future, but I think there's enough there to represent a starting point for anybody who really wants to have a multi-grid solver in the pencil code. Basically, for the Laplace equation, the multi-grid solver is in place, but currently only for the simplest boundary conditions. So if you really want to use that, you have to do a bit of work, and if you want something more fancy, then you obviously have to adjust to adapt it. But some of the groundwork has already been done. Let's see, is that good? That actually go to this one here. I'm not sure you can see much of this, but basically what you can't read here is the recipe for doing multi-grid speed. So what this says is you start with we have a grid, which is ideally relatively fine, and we want to solve something like the Poisson equation. So we have Laplacian, for example, Laplacian phi equals density, essentially. And we already have ways of doing that using Fourier transform in at least two coordinate directions. But that is limited to certain kinds of boundary conditions. It's actually not as bad as you might think initially. The boundary conditions don't have to be periodic for Fourier methods to work. But if you want to use Dirichlet conditions where everything is zero on the boundary, you'll have to also change the method, because then you need Fourier sine transforms instead of Fourier cosine transforms. And basically, if you want to, it's coded now for periodic boundary conditions, and if you want to go beyond that, you'll have to invest some time to get this right. And it's not that flexible still in terms of boundary conditions. What made me code a multigrid solver was actually not the boundary conditions, but it's the fact that Fourier conversion of the Laplace operator only works if you have the Laplace operator, the Laplacian, without any space-dependent prefactors. As soon as you have space dependencies in front of that, let's see, well, that you cannot easily get rid of, you're basically doomed if you try to apply Fourier methods. And multigrid can handle that. I'll show you the equations at some point. So we have our grid, say, I don't know, 256 cubed, and we want to solve the Poisson equation. So the one standard method of doing that is to discretize with a 1, 2, 3, 4, 5, 6, 7-point stencil. So you just do second order, second derivatives in all 3 directions. And then you solve for you write down that discretized Laplace equation, you solve for the value at the central point, and you iterate that over the whole grid. This is very efficient in getting rid of small scale deviations. So whatever initial condition you start with, the small scale stuff gets stamped out very quickly, but the large scales take ages, and literally ages, if you really try to use that method with significant resolution. What the multigrid method does is it uses that operation scheme. Then on the finest grid, on the original grid, it gets rid of the smallest scale deviations from the solution that you're looking for. And then you map the information you have on that grid to a coarser grid. And now, again, you get rid of the smallest scales of the stuff that is near the Nyquist scale. But now it's a Nyquist scale for the coarser grid, because you don't have, on that grid, you don't have the information of the finer grid even. So now you're getting rid of effectively larger scales than your delta x. Now you're getting rid
You
of...
have, of course, plots in
delta
the
x.
documentation.
Hmm?
You have plots. I saw plots in the... That is W. Yeah, that one.
Yes, okay. So you're okay. This here is the finest grid. Then you have the coarser grid. So here you have a grid facing h, delta x or whatever. Then you have 2 delta h in the simple space, 4 delta h, 8 delta h, 8 h, and you can go on. And so you from the fine grid go to the you either now or on the way back, or normally in both cases, on both ways, you do one of these iterative steps with a Gauss-Seidel iterative scheme, or maybe a weighted Jacobian scheme. Gauss-Seidel is more natural when you deal with real computers. So you use one of these schemes that gets rid of the scales that are close to that grid spacing H, and then you map your problem to the 2 times coarser grid, and then you get rid of the scale and all the scales up to and somewhat above 2h, and then you go on to the same thing with 4h, and you go all the way until you have effectively only a few grid points on the very coarsest grid. And if you iterate there, then you basically very quickly get the large scales right. And then you go back and interpolate the information that you have on this grid onto that grid. You add the information that you calculated at this point, and you just go back to the finest grid. And you do many of these sweeps. In the tests I did, something like 20 or 30 sweeps was needed. But that is then essentially independent of the resolution that you have. Which is related to the fact that there is way fewer points on the coarser grids than on the finer grid. So even if you go all the way to infinity here, you still get only a finite workload to the whole thing. And with a bit more detail, we start, and I know you can't read that, but I don't really care. We start.
Can I make a figure, no?
I'm not sure. Yeah,
Just what's that presentation about?
From the top, from the linear.
oh, there is, yes, there is a
Go.
magnifying glass.
Wow.
So, what you do if you have just two grids to start with, is you start with a guess on the fine grid, and that guess, if you're lazy, will just be your function phi, maybe I should write down the equation we're solving after all, is equal to 0. So we have nabla squared f, if I stick to that notation, equals g, and this here can be function of x, and this one certainly is. Can you read that, or should I use a different color? Not that bad. Or is it? Then technically what you do is you calculate the residual. So you have that, you have mapped this equation to a linear system L F L H F H equals GH. That's a discretized version of that. And L now is a matrix that mixes each grid point with the neighboring points. And to just invert that matrix is practically impossible because there's so many grid points and it's a sparse. There's a very large sparse matrix if you really want to write it out. So that's why people are using these iterative schemes. And we only have an approximation now, f hat, which is, ideally it would be close to the solution. Actually, initially it's way off. So we can plug that into we can feed that to the operator and look how close do we get to the right-hand side, and the difference is residual. And then we take that residual and interpolate it to the coarser grid, or map it to the coarser grid. And there's known good ways of doing this, and they are simple if you have a textbook setting, and they are considerably more difficult if you do it for a real code like the pencil, but I'll talk about that. And then you solve an equation on the coarser grid. This is now capital H, if you can see that. You solve an equation where this residual is on the right-hand side. On the left, you have a coarse-grained analog of your matrix of your derivative operator. After all, you discretize Laplacian, and then you take the solution that you get here. Well, let's assume you have that solution on the coarser grid. Let's assume on the coarser grid you can solve the whole thing. Take that solution, you interpolate it down on the onto the finer grid. That's called. I won't get into the nomenclature because nomenclature is what is really the most difficult thing about multi-grid. You effectively fine-grain that, and then add that to that initial guess that you were starting out with. And after going back to the finer grid, you do one downsider iteration step. Typically, one also does one actually before going up to the causal gradient. But there's all sorts of variants. You can do it only on that side, only on this side. You can do it once here and 7 times there. And I think many people have their personal recipe that they guard more than their kitchen recipe. It doesn't make a big difference.
Since you mentioned just outside here, you also mentioned another scheme earlier, and then you did not mention successive over-relaxation. So there are 3 different methods. They are all related, I suppose. So what is the other method you mentioned?
Weighted Jacobian iteration.
Is that then perhaps the same as successive over-relaxation?
I
So
honestly
clarify
speaking
first of all-
don't know what successive over-realization is. But I think that's significantly more involved. It's
so that means successive over-relaxation means, of course, that the